So in this experiment, what we're going to do is we're going to look at 12 different solids, examine their physical properties, and see if they are metallic, ionic, nonpolar covalent, or polar covalent. So for this video, I have 4 of those solids shown. The first thing that you want to do is you want to take note of the appearance. So we can see that with solid 1, it is granular. It's not a powder. There's definitely a little more crystal-like, but obviously it is white. There's no color to it. For solid number 2, though, if you can see, this actually is a bit more powder-like. It doesn't look crystalline. For solid number 3, we see that it has this light gray color. And then for solid number 4, we have, almost these pellets. Again, not a powder, not crystalline. So we want to write all of that down. We can see that 1, 2, and 4, they're all white solids. But if that's all we say, then we miss some of those important descriptions that can help us distinguish between the different solids. Now, we're going to do a lot of different tests, but the first test that we want to do is we want to test if it is able to conduct in the solid state. And the reason for that is I know that only metals conduct in the solid state. So if I see that something is able to conduct when it's a solid, I don't need to test any of the other properties. I don't need to go through the melting point, the solubility, the conductivity in solution. So what I'm going to use here to test the conductivity of a solid is this conductivity tester. You can see it has the electrodes here at the bottom and just a simple on-off switch. There are instructions on the back. So there's 2 lights here. There's a red light and a green light. Whether or not one light or both lights light up will tell you if it's able to conduct a little bit or if it's a good conductor. So we need to be able to put this against each of those solids. Now this doesn't fit very well in the beaker here. So what I'm going to do is I'm going to pour some of the solid onto a small weigh boat, like so. And I'm going to make sure that it's on. And we can see that, I have it immersed in the weigh boat, in the solid here, and it is not lighting up. So solid 1, not able to conduct in the solid state. Okay, so now I'm going to just wipe this off. Let me grab a paper towel. Right, we don't want to contaminate our solids. Now I'm going to take solid 2, do the same thing, because again, the probe doesn't fit very well in the beaker. Now again here, we're seeing it's not lighting up. So this is telling me that solid 2, not a metal. Probably also can get that from its appearance, but we still want to just make sure that it's not conducting in the solid state. All right, next we have solid 3. Now this I can get to touch, because the pieces are a bit bigger. And so what you should see, if I can get good contact here. There we go. So you see it kind of, there we go. So you see it's lighting up now, right? Just have to make sure you get good contact with the solid. So the fact that solid 3 is conducting in the solid state, and also just from its general appearance as a shiny gray solid, this is telling me that solid 3 is most likely metallic. So I don't need to take solid 3 and do all of these other tests that I am going to have to do with these other solids. Okay, and then lastly, we're going to test solid 4. Okay, same thing, try to get good contact. And we can see it is not lighting up. Okay, so at this point, I at least know of my 4 solids that number 3 is metallic. Now what I'm going to do is figure out their melting points to try to determine if it is non-polar covalent as opposed to polar covalent or ionic. So the next property that I'm going to test is the melting point. I know that non-polar covalent compounds should have low melting points because non-polar covalent compounds, they have weak intermolecular forces, so it doesn't take a lot of heat to overcome them. Whereas polar covalent and ionic compounds tend to have much higher melting points. Polar covalent because you have stronger intermolecular forces. Ionic has a high melting point because, not because of intermolecular forces, but because you would have to break the ionic bond in order to melt an ionic compound. So I'm going to test for melting point a couple of different ways. The way I'm going to see if it has a low melting point is by using a hot water bath. So I have some boiling water here, and then there's steam up above. And so since I know that water boils at 100 degrees Celsius, I know that that's the temperature of the steam. So what I can do is I can put a little bit of the solid into this aluminum evaporating dish and simply hold it over the hot water bath. If the heat from the hot water bath is enough to melt the solid, that tells me it is likely non-polar covalent because 100 degrees Celsius would not be enough heat to melt an ionic compound for sure, and most likely not even a polar covalent compound. So what I'm going to do is I'm just going to transfer just a little bit. I don't need a lot. So this is sometimes what we call a pea-sized amount. You can see, it kind of fell. Hold on. You can see there, just a little bit. And I'm just going to hold it over the hot water bath for a couple of minutes and then see if it melts. And I'm going to do this with solid 1, solid 2, and with solid 4, and then we can see how it looks. All right, so at this point, I've tested these 3 solids, holding them over the hot water bath to see if they have a low melting point. What I can see here from 1 and 2 is that they did not melt. So that tells me that solid 1 and solid 2 do have at least moderate, if not high melting points. But solid 4, we can see, you know, these little puddles where those pellets have melted. So solid 4 did melt, so it has a low melting point. That tells me that it is most likely non-polar covalent. Now I'm going to confirm that by testing its solubility in hexanes in a little bit, because hexanes, being a non-polar solvent, should dissolve a non-polar solid. Remember, like dissolves like. But for right now, we're going to put solid 4 off to the side. We'll come back to this when we do solubility. But solid 1 and solid 2, I do want to see if I'm able to melt them. And so to see if they have a moderate melting point as opposed to a high melting point, this is where I'm going to use the Bunsen burner. Okay, so what I have here is I have my iron ring, and then the wire gauze is so I can rest my solid over top here, have my Bunsen burner underneath. So I'm going to light the Bunsen burner. Okay, adjust the height of the flame. Right, I don't want the flame shooting up over the iron ring. And then I'm going to put solid 1 up on the wire gauze. And I'm going to let this go, just like with the hot water bath. I'm going to let it go for about 2 minutes to see if it melts. If it melts, that tells me that it has a moderate melting point, making it likely to be polar covalent, but not necessarily. Some polar covalents do have higher melting points, or certainly ionic if it doesn't melt. So test this for a couple of minutes. When I'm ready to take it off, I'll use my crucible tongs. Obviously, it's going to be warm, so I can get it off of the iron ring. All right, so I've now tested the melting point using the Bunsen burner, and what we can see here is that solid 1 still did not melt. Same with solid 2. So neither solid 1 nor solid 2 melted. But again, the difference between ionic versus polar covalent isn't necessarily going to be determined just from melting point. So next what we want to do is we want to test conductivity. So move these off to the side. We know that ionic solids should be excellent conductors in aqueous solution. Polar covalent compounds, if they are acidic, could have some conductivity due to the H plus ions, but they shouldn't conduct as well as a ionic compound, assuming that the polar covalent compound is a weak acid, not a strong acid. So I took a little bit of the solids, put them in different beakers here, and I'm going to add some deionized water. Okay. And then I'll grab the rods. So what I have here, this is a different way of testing conductivity than using the probes that we were using earlier. So we're using the lab quest here. So I'm going to zero out, just like using a balance. So I'll go to sensor, zero, kind of zero out the conductivity. The units here are milligrams per liter. And then here I have my probe. So I'm going to put the probe into each of the beakers and see what number comes up. So let's start with number 1. So what I see here is the conductivity here is very, very high. So it's reading above 16,000. That is telling me that solid 1 is most likely ionic. This has incredibly high conductivity. As we know, ionic compounds are strong electrolytes. So most likely solid 1 is an ionic compound and not polar covalent. Right. Now I want to rinse this probe. And I want to try solid 2. Now we can see that solid 2 does have a little bit of conductivity here, but it's nowhere near what solid 1 was. So this is reading, around 450. You can see that the number will kind of fluctuate a bit. We're really not interested in the precise number. This is a qualitative lab, not a quantitative one. So what I'm more looking for are differences between the different solids. So I see that this does have a little bit of conductivity here. It's certainly not 0, but it's nowhere near the 16,000 of solid 1. So most likely solid 2 is going to be polar covalent. Now, one way that I can try to confirm if my polar covalent compound is acidic, not all polar covalent compounds would be, but one way I can determine that is by simply using some litmus paper, some pH paper. It'll change color depending on the pH. So I'm gonna dip this in here. And what we can see is that it turned red, indicating that this has a pH of 1. So it is certainly acidic. So it is likely that not only is this a polar covalent compound, but that it's also an acid. And that's why I had a little bit of conductivity there. It wasn't 0, because we know that acids donate their H+, and so those H+ ions are likely what was causing the conductivity to read around that 450. One of the last properties that we want to test is solubility. So we know that nonpolar covalent compounds shouldn't be soluble in water, since water would be a polar solvent, but polar covalent as well as ionic solids, those should dissolve in water. So we can use the same beakers that we were using to test conductivity, since we added water to them. And what we can see is that solid 1 very much dissolved in the water. Solid 2, some of it dissolved, but we still see a lot of solid floating around. So this really only has moderate solubility in water. So while it is likely polar covalent, it might have some non-polar parts to its molecular structure, and those are just not dissolving in the water. Now, solid 4, remember we classified solid 4 as saying that it was likely non-polar covalent due to its having the low melting point. So in order to confirm that, I added hexanes to the beaker as opposed to water. And what we can see is that solid 4 did dissolve in the hexane. So this was a good confirmation to say that solid 4 is likely non-polar covalent. So with solid 1 being ionic, it was soluble in water. If it wasn't soluble in water, we would go on and see if it's possibly a carbonate. Carbonates are not terribly soluble in water. And a way we can tell if something is a carbonate is to react it with hydrochloric acid, in which case it would generate CO2 gas. So we would see bubbles form. I don't have to do that here because the solid did dissolve in water. But if you're testing and your solid does not dissolve in water and yet had a high conductivity, you want to see if it's possibly a carbonate by reacting it with hydrochloric acid. So now that we've tested the properties of our 4 solids, we want to clean up and then have a seat and fill out our results table, deciding if the solid is metallic, non-polar covalent, polar covalent, or ionic.